So now let's get back to recursive definitions and see some very interesting things that you could do with them. So first, let me just show you closed form of some sequences, just kind of to remind you after the last lecture what those closed forms look like. So for example, for arithmetic progressions, you didn't really need the recursive definition if you knew that to compute the nth element of the sequence, you just need to take your initial element and add n times d. Geometric progression, very similar, except now instead of adding, you're multiplying. And instead of taking n times d, you take r to the power of n. But what about the Fibonacci number? Does that have a closed form? It does have a closed form, and it's a very interesting one. So the closed form of the Fibonacci sequence is something that at the first glance doesn't seem like it would have anything to do with, well, a list of very well-defined natural numbers that Fibonacci sequence is. Because the way the closed form is defined is in terms of the golden ratio, which is some number which involves square root of 5. But why involved would something like square root of 5 come in to Fibonacci number? What is the significance? And why does this strange number, 1 plus square root of 5 over 2, have a name? Well, that number, pronounced phi, is the famous golden ratio, which is defined as a ratio such that if you have numbers a and b, then a plus b over a is the same value as a over b. So for example, in this picture, the green line plus the blue line is the same length as that red line, but then pink and blue is the same length as green, and so on and so forth. And you see how this already starts forming very interesting patterns. And one thing about Fibonacci numbers, which will get us into some really cool pictures that we are going to see in this lecture, is that it seems that a lot of things that you see in nature do express this very golden ratio. This was something that a lot of artists and scientists were interested in during Renaissance and other time. It is pretty cool. Like if you look at the shell of a snail, then there is actually a relation between different parts of that shell, which is indeed the Fibonacci sequence, like in this picture. So it starts small, then gets bigger, 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 and the rate in which it gets bigger is exactly the golden ratio, which means that it ends up forming pieces of sizes of the Fibonacci sequence. So this is kind of the theme for this lecture, but before we go into the cool pictures, let me just first expand our notion of what it means to recursively define something. Because so far we only define functions and sequences of primarily numbers, even though we saw some examples with sets. But there are all sorts of things that can be defined recursively. So one definition that you already seen is the definition of a sum. I could just define what the summation sign means by saying that a sum of I from a number to the same number of I, of f of I is equal to m, and of f of I just equal f of m. And similarly, the product from m to m, it just equals f of m. But now we can apply recursion and say if we want to compute the sum from the sum of the values of f of I for I from m to n plus 1. We'll have to compute it up to n and then add f of n plus 1. And similarly for the product. So you see here we define something which is kind of a different thing. It's not quite a sequence, it's not quite a function. Well, it's kind of a function by using recursive definition. And this sort of suggests that you could use recursive definitions to define all sorts of objects. And one object that we are going to define here is fractals. Actually, the whole description of what a fractal is kind of suggests recursion, because a fractal is a self-similar object. That if you take something like a fractal and you zoom in on it, you're going to see something that looks like the whole thing. And you keep zooming in and you keep seeing what looks like the whole thing. For example, if you take a leaf of a fern, which is kind of natural approximation of a fractal, then if you look at that little part of a leaf, it essentially has the same structure as a whole. I mean, at some point it goes down to being really much too small to be developed into something like this, but mathematically the processes that govern it are kind of the process that recursively generates a leaf. There are lots of fractals that you would see in nature. Some of the very first animals were essentially developing in a fractal way before we got our bilateral symmetry. Other than the fern leaf and the really cool vegetable called Romanesque broccoli, there are fractals in things like mountains and stock markets. How would you see fractals there? Well, they're also self-similar, because if you zoom in on the mountain range, you will see a little bit of a mountain range. You zoom in closer and closer, you see a rock which kind of in itself looks like a mountain range. Similarly with stocks or a lot of graphs that you would see if you're doing data science, if you zoom in on a graph, you kind of see a similar pattern to the whole graph. That was actually how a lot of the fractals were discovered, by looking at behavior of graphs and noticing that if you zoom in, the graph still looks very similar. So just to show you a little bit more how that cool broccoli thing looks like, here is a zooming in on that broccoli picture, and you can again see that this vegetable, this plant, was growing very recursively. It's sprouting those little cones that are covered in cones, which are themselves sprouting even tinier cones, and then you end up with really cool structure. And if you live in a big city, sometimes you could see those broccolis in the supermarket. They taste like broccoli. So far we just talked about cool pictures and where they occur in nature, but let's get back to kind of computer science view and say, okay, so maybe I want to generate for my game or background or something like a mountain or a plant or something else. How would I do it? So for that, let's first look at fractals that are defined kind of simpler, just in more mathematical way. And here are some examples. So probably the simplest here is the Sierpinski triangle. We take triangle, break it into 4 triangles, cut out the middle part, and then continue with the part that are not cut out. It's again very much a recursive definition of an object, and if you do a few iterations up to the point where you cannot really zoom in more, you end up with something like this. Fractals are also used both by nature and by people to build things like space-filling curves. A line which winds around and around and fills up all available space while having a pattern. And this is very, very useful for all sorts of things, from transistor design to all sorts of things. And you find it in nature too, because things like lungs, for example, they do have some properties of space filling curves. And one of the more famous fractals, one that comes from a pretty simple equation that just being again computed recursively again and again and again, is the Mandelbrot set. And this one you may see online if you see pictures like that. So at the first glance it doesn't look very fractal, because it's this kind of combination of two black blobs with a spike. So there is fractal in that. But as you see, as you're zooming in, you keep encountering this weird shape, the two blobs in a spike shape, over and over and over again. And around it you have all those cool structures, the spirals and other interesting formation. There is a whole science around it. And all of it comes from working with, well, recursive definitions of something. This thing is computed completely by just recursing. So let me show you what I mean by computing things recursively. And let me show it on a probably simpler fractal, the one that we've seen, called the Koch curve. You could also put 6 of those together and get a Koch snowflake. But let's just start with the Koch curve. Here's how you build it. The basis is just an interval. And then for the recursion, first you split this interval into two pieces, and then kind of imagine building an equilateral triangle on top of the middle third. So you end up with triangle with three sides, each of which is 1/3 of the original interval, and then you remove the bottom of the triangle, which was the part of the original interval. So now you got 4 intervals, and now you repeat the same process for each of them. Each of those 4 intervals you break into 3 pieces and replace middle third with 2 pieces of the same length as the middle third. And then you keep going, and eventually, again, you could think about it as going to infinity, but truth is you are not going to see much improvement in your pictures once you reach pixel level. Eventually you see something that looks like an interesting smooth curve, Koch curve. Something very cool about Koch curve and a lot of other fractals is this. So if I show you a line and I ask how many dimensions it has, you say, well, okay, it's a line, it's one-dimensional object. Maybe if I show you a picture on the second stage, you say, well, it's 4 pieces of a line, it's a one-dimensional object. But as you keep doing this process to infinity, it becomes less and less and less one-dimensional. So does it ever become two-dimensional? Not really. It will, as you keep doing it, become something of an infinite length, and its dimension will be somewhere partway between 1 and 2. It would be log base 3 of 4. You could kind of see where 3 and 4 are coming from, right? When you take something, break it in 2 and replace it with 4 pieces. And this is a property of a lot of fractals. When you start with one-dimensional thing and you end up with something higher dimension, and part of the reason fractals are fractals is because they have that fractional dimension. So if you want to play more with fractal, there is a cool program. If you go to that URL, you should find it. It's just a Java program, you could run it, and that will allow you to play with a lot of different fractals. You could do the ones for the setting that the program has, or you could play around with the settings. It's not that difficult to figure out what the thing is doing. So let me show you some pictures generated using this program. So here's one example. Here is a basis. We start with a line. We apply one step of a recursion and ignore the letters. They just tell you the rules how to do it. But you replace this line with the line plus one thing sticking to the right and the top split in two. Okay, now you know the drill. You take every interval and you replace it by this. So here you have 3 intervals sticking up and you replace each of them with a shape. Do it again and again. And you know what? If you would have shown it to me, I would say, oh, that's a picture of a plant. You probably photographed it somewhere in the wild, right? If you're a very good artist, well, if you're a good artist, you could probably paint something like that or draw it. But to me, it's much easier to write a program that would draw something like that than actually take a pencil and reproduce it. So just to reiterate what's happening here, we start with a basis which is just one line, and our rule essentially takes a line and converts it into the shape that we see in the stage 1. And in stage 2, we take every line sticking up, we ignore now the original part, and we apply to it the same rule. And then we keep going. Every time every piece of the original becomes a piece with 3 sticks, and every sticks become a piece of the new part. So let's do another example. So we also start with a line, but now instead of replacing it by this piece with 3 sticks, we replace it with something like this. We bend it and add 6 lines coming to the sides out of it. And then you again repeat it. So each of those 7 pieces, you apply the transformation to it. And already at stage 3, it starts looking fairly realistic, like something you could see in your backyard. By stage 5, only 5, it's not like too many stages, you end up with something that looks very much like it came from nature. I wouldn't even try drawing it with a pencil, but generating it will really only take 5 steps.